So, good evening, guys. So, this is the lecture number 12 for this computational physics course. If you remember correctly, what we did in the last lecture, so I'll briefly summarize this for you. Let's not waste too much of the time. So, its last lecture was about the second order differential equations, and we basically describe what sort of methods we can use for that. And there was adaptive approach. It was basically equivalent to the first order methods, but it's just that we divide the second order differential equations into the simultaneous first order equations, and then we use the similar methods we do for the other stuff. You know, the idea for these kind of stuff is also, kind of similar. So why is it similar for the partial differential equation? The partial differential equation, there are also independent coordinates, but now you have the definition of partial differential equation is basically varying one variable, which is being uh, taken a variation in, right? So we will see the methods are not just, something unique. They are just the follow up of the methods we usually study. So now in physics or in other sort of fluid mechanics and in various biological stuff, you might encounter a lot of partial differential equation. For example, as a physicist, I would say the kind of equation which I encountered were like wave equation, diffusion equation, the Laplace equation, Poisson's equation, other Maxwell equations. All of them involves the partial derivative, even then the Schrödinger equation. So what I'm trying to say, all these equations are sort of partial differential equations. Now, just like the ordinary differential equation, we divided these things into initial value problems and boundary value problems, or both, right? That was the idea. Just making sure those things are being recorded. Yeah. So even in this case, this is the case. So there would be a boundary value problem. For example, if you have a box or a sheet where a particular side is at the potential V and all other are grounded. So 0, 0, 0, but this is at V. So if you want to find the potential at any, you would have to do the Laplace equation. And the with the boundary condition. So these are the kind of equation where you will encounter only the boundary conditions. But in most general cases, you can also have initial value problems or the combination of both that we will see in the time limit. So for example, let's start with the Laplace equation and try to see how does one really go about solving the partial differential equations. So, in physics, you define the electrostatic potential. Phi, the E is described like this, and your Maxwell equation is this. first Maxwell equation, and then you say put over there, you get the del square phi equal to 0. Where is it? Del square phi equal to 0. That is nothing but your general Laplace equation. So this basically tells you the how the potential occurs at all the spatial coordinates, right? That's what the potential follows. So potential is something which follows the Laplace equation. Now, for example, if you have in 3D, so it would be like this. Now, this is basically a boundary value problem. Now, what is the example of initial value problem? For example, the wave equation. In the wave equation, you have both the second derivative of and you have both the x and you have some constant, right? So in that case, you would need also the time. You want to find it at a particular time. For example, if you have a string bounded between these, this is a fixed points. These would constitute the boundary condition. This is also boundary condition. Now at t equal to 0, let's say t with t equal to 0, you give a pluck. So this is the u at, this is the initial condition, right? And these are the ut0, ult0. This is at all time, this has to be 0. Okay. So this is sort of the combination of both the initial value problem and the boundary value problem. So let's start our topic today with the boundary value problem. How to solve. For example, just start with the Laplace equation. Now we will describe a method of finite differences. Now, first thing that really comes to your mind is finite difference. Why? Because there are partial derivatives involved. So if you have the partial derivative involved, you can write them in terms of the central differences. So let's say consider the 2D version. Okay, so this is the 2D version of the Laplace equation. And now the method of finite differencing that involves you divide the space into a grid of the discrete points. Now usually we use the uniform grid, but there are the cases where you will be end up using the very non-uniform grid depending on the requirements, right? So for example, you have this square sort of sheet, let's say this is v, this is 0, this is 0, this is 0. What you would do, you would make a grid okay. Then so if you have a grid now what your idea is, you write the partial derivatives. How would you write it using the central differencing? Okay, now you put back in the equation. What would you get? So now how does this look like? So you wanted any xy, you would have to take the average of the 4 points around it. So it's like this. You have the xy, you have the x plus ay, x minus ay, xy plus c, xy minus c. Now, this is basically, if you look at the rule of the equation, this is 4, this is minus 4, sorry. This is 1, this is 1, plus 1, plus 1, plus 1. That's the sort of the rule that the Laplace equation should follow, right? Now, one important interesting observation is it doesn't depend on the A, whatever the grid spacing you use. But you know one thing, that when you do the method, it would depend the number of the grid points you use. That is something which will decide how fast your things is gonna converge. So it doesn't depend on the E really, but it is about the number of grid points, which is equivalent to A, right? So what is happening over here? If you see, it's basically decomposed into the set of the simultaneous equations, just like that, right? There are lots of simultaneous equations around every point. Okay, so this is the sort of the equation you have. Now, now you know this sort of equations, how you're gonna do this. You would either the first method that we discussed in the root solving was the relaxation method. You give a guess, you find it until it converges to the fixed value. But there were some intricacies over there, there were some caveats. So, what were those caveats? These were like your solution might not converge. There was some rule which would decide the convergence of the solution. But in the case of this sort of equations, it's not really the case. Basically, in most of the cases, it will converge. Okay, so, so what I'm saying, you have the boundary conditions, right? You have boundary condition B on the top of the thing and 0 otherwise. Okay, on the other walls. So guess inside the box. Let's say your guess doesn't have to be very good ones. Let's say you guess all of them are 0. Okay. Now what would you do in the first iteration? Using this equation, you would find at every xy what is the value of phi using these values. Okay, you have n cross n grid. You find a new n cross n grid using the guesses you have and the boundary condition. And there is one more condition you would have to put in the loop, that you are never going to change the value of the potential at the boundary, which is an obvious thing to do because that's what has to be kept fixed during the whole course of the solving the problem. So far, so good. So now the next thing is, now what would you do in the next step? You would change the array which you have, or you would swap it with the new one, which would contain the modified phi's which you have found using this equation. Okay. Now, then what? You have new guesses, sort of. You have new guesses. Now, using that, you would start at every point again. You take the average around the 4 points, and give it that value. You would keep on doing this n cross n calculation every iteration until the your phi until your phi xy minus becomes the target accuracy. Okay, so yeah. Now there is one issue with this. You would understand that, like, okay, this is fine for this. Then that I will discuss. Now, what you are gonna do after this? There is something called over relaxation, which you would practically you should use. But before that, let me also write the method for the Poisson's equation. So Poisson's equation may, instead of the potential boundary condition, you would have somewhere the charge in your system also. The electron density or the charge density which you have in the system is not zero now. There is a function of x and y. You would have the rho. So for example, if you have this potential, the one we were discussing, let's say at these sort of xy and at these sort of xy, some plus, you have some minus. Okay, so basically rho of xy is non-zero at these sets of points. Fine. So then in such cases, what would be the change? It's basically your Laplace equation is now the this is the equation. Now in 2D, again the solution would be this. In terms of finite difference, now your phi xy would be this. With a term which is now dependent on the E as well, right? So there is something which is different over here now. Now you would have to also choose the A carefully. What would be the A that you would be needing for the conversions? So there are some rules which I'm not going to discuss. So the things how you should choose your A, but which is for you to figure out. Um, so there is an example in the Mark Newman, and you would actually find out what the thing you should use for that. Okay. So this is similar. You would do the way you were doing it. So using the row over there as well. Now that's how the poisons would be solved using the relaxation method. Now these would become very slow. Why? Why it would be very slow? For example, this simple problem of this V00 that would be taking you around 10 minutes to solve this on the computer with 100 cross 100 grid. Now, right. But if you look at the algorithm very carefully, you would see that there is something which you are doing which you should not be doing. I mean, something which is a waste. Now, what is that? At every iteration, you are finding the psi xy from what you have from the old array, right? Of the psi xy. And then at every xy, you have this new thing and you put it in a new array. So you're dealing with the two arrays in this case. Okay. What instead you should be doing was you just update it. And for the other one, you use this updated value for the averaging instead of waiting for everything to update first and then updating it in the next iteration. Okay, so now you would realize one thing would be it would reduce your thing a lot and you would fastly converge because you are taking care of the modified potential at every step. Okay, now yeah, that's what the Gauss Seidel thing would be, which I will discuss. But before that, there is something really important to make it faster. I would be describing that is the over relaxation technique. Now, over relaxation, what does that really mean? For example, at a certain xy, your solution, the converged one is zero point 0.5. You started from 0.1. In the next iteration, let's say you go to 0.3, and next you go to 0.3301, you go to 0.302, and till that you after many iterations you go to 0.5. So basically it is taking time to converge, right? In that sort of process you are wasting a lot of time. Now there is this way, what if you increment the potential values at every point by a certain factor so that you hope that you will actually reach close to the solution and you don't have to put more iterations to reach there. Okay, so that's basically over relaxation as the name suggests. You relax and you do it over a lot at some steps. Now, why is that? You want to reduce the iterations over there. So, for example, how would you formulate the algorithm for this? So, you would call your new set as this. Okay, now this delta phi is basically the increment at this step. Okay, now instead of you would increment it by the value which you calculate from the relaxation method, right? Now define the set of the normal way. So you put a small factor with it, omega. Okay, you're saying I won't increment by 1 times this, I would increment by let's say 1.5 times this. You're saving a lot of time with that, actually. Okay, so the omega is greater than 0. So if this is the case now your this thing would be yes, if we look at this would become okay. Now in this case, if you see omega 0, this would be the normal relaxation formula. So you're now incrementing by omega. Okay, that's how the now this you would realize this is much faster than the normal relaxation. You call the normal relaxation as Jacobi method. Okay, this is good. This is really good. Now, your next step is, as I described, what you're doing in the normal relaxation method, what you do, you find at a particular iteration the potential at each grid point one by one, and then all of them are put into a new array. Then you repeat the steps again. Okay, so now if you assume uh, you don't use the old method, so you don't use the old values when you modify any particular value. So it's like if you have a grid at a particular iteration, what I'm saying is you have started from here, you find the new one this, new one this. Now for finding this, you would use the new of this. You are not going to use the old one. So that is a much better version of the Jacobi method. So you don't really care about the old ones. Every grid point you use the new ones for the neighboring. Now you do the same thing with the whatever we have done. You would do the same thing using this grid. Okay, so this is how your ghost title would work. Now, in the last part of this lecture, I would give the introduction to the initial value problems. Okay, now for that, I would write the heat equation in one dimension, or you would say the diffusion equation. Now, if you see this equation, you can't discretize time, right? On a grid, you can discretize, but the way you do discretization for solving these partial derivatives in x, you won't be really doing the spatial discretization for the time, the temporal discretization for the time. Okay, so that's right. So let's say that there is not the idea would be to create space-time grid, which is little silly over there. You would definitely create a space grid as well, even at this time. But for time, what you would use is you would use the normal ordinary differential equation techniques. So let me show you that. So it would be like, that is called FTCS method. You would do the finite differencing for this. You put in the equation. Now what do you have? You have a differential equation in t, right? You have a differential equation in t, but it's not just one differential equation. Again, for all the x's, you have the simultaneous ordinary differential equation in t. Now, what is the rule that comes to your mind when you want to solve such differential equation? Euler, Runge-Kutta, all these things you can use. But you know, the interesting thing is there is no point using Runge-Kutta over there. Does anyone know what's the reason? The reason is simply because you are using the finite difference, central differencing for the second derivative, which is already the error correct up to the second order. Okay. So what the point is, Why would you use the for the derivative something which is correct up to the order 4? So because there is already a error of h squared that is in this finite differencing. So it would be just simple better going with the second order Runge-Kutta or just the Euler method. Even the Euler method would be just as simple as that, would be doing okay with such equations. So let's just write this equation for that. So now your equation is simply this. You can convert it into the for the normal derivatives. Now you can always write. So your thing would become, this is your equation. That's how you will be just solving such initial value problems. So yeah, these are easy to solve. You can write simple problems to do all of this. Yeah, I should have discussed the numerical instability for all this, which we will be discussing next time, because yeah, choosing certain order of the h, you can get the numerical instability. So if you use, this is something you have to use, stable h for the h. And I would discuss this condition next time. Why is it so? And it's very simple, you know. So we will spend some time doing all the stuff regarding the numerical and stabilities next time. Okay, this looks clear. So, right. So, thank you. We can end for the day. So, see you next time.